Am I audible? Okay, thank you very much. Before starting this lecture, let me once again give the perspective that what we have done in the last class. Welcome to the lecture 5 session 2, and this is let me just give you once again quickly give you the perspective that what we have done till now, okay, and what is the way forward into this lecture. So number one thing that we have seen that we have a problem, okay, we have a problem such as such as 8 puzzle. Okay, what is the 8 puzzle problem? That there is a place and a lot of numbers are there. Say I say 2, 1, 3, 4, 5, 6, 7, 8. Okay, these numbers are there, and there is one place that is vacant. Okay, and what you can do, you can the places which are nearby this vacant place, you can shift them. And then if let's assume that you choose to shift 6 over here, so what would happen? That you would reach into this configuration, that you would be here 6, 1, 5, 7, 2, 8, 4, 3. Okay, and there the blank space would come here. So we told you that if you have a problem, so you can say that this is the state 1, this is the state 2, and similarly you can find out what all the states are there. And then you can say that if you are into state 1, you take the 6 value 6, move right, then you reach to the stage 2. And similarly you can do for all the states that what action you take and how you go from one place to another. Okay, so this defines a graph. So you understand that given a problem, you can find out states, state space, and from this state space, you can make a graph. Okay, then you want to find a solution. And what is the solution? Solution is this, that I am going to give you this configuration, and let's assume that how to go into this configuration. Okay, then your task is to find out that you come here, do all these things, what actions need to be done so that you reach over there. Okay, so we have seen that to find the solution you have to do a search. Are you with me? Okay, are you with me? Okay, you need to perform a search. You are with me? Okay. To do this search, there are two ways. That when only this much information, that what is the state and their connection, only this information is available to you. This is given to you. This is called blind or uninformed search. So we have seen that various blind and uninformed search into the previous class. Then we have seen another approaches that are called informed search. Okay, and one of the algorithm was A star. We have seen that this algorithm is optimal. Means if we want to minimize something, we just don't want to find out the path. Also, we want to find out the minimum path. So this algorithm is going to give you the minimum path, number one. Also, it is going to give you the solution. Both the things it guarantees to you. That is going to give you the solution if it exists and it is optimal. Then we have discovered that there is a problem, that this algorithm proceeds as the DFS, very similar as the DFS. So we should do something to save this algorithm from being as DFS. which sometime may not give the solution. Okay, give the solution because the depth is infinite. Because the depth is infinite. We have seen this in the last class that one algorithm that how we can do this. After that, we would be seeing some other things, other problems of the A star, that how to solve those problems for the A star. So when we would be finishing that part, then by that time we would be convinced that A star is being an optimal algorithm can be used to find out the solution using the heuristics. But one question remains, and that question is that how to find out the heuristic. How to find out the heuristic function itself, because Gn we can find out at every step, because whenever we are at some state we know that how much we have spent, and that is Gn. But how much it is expected to take more, that is called the Hn part, and that is difficult to tell, and that is the heuristic function. How to find out this value, this we would talk later into this class, and by that, and then we would be actually completing this part, that given a problem we have formulated them into right way, and then we have applied heuristic to find out the solution. Okay, this part will be completed. So we have done till this particular point, and later we are going to see that what are the some of the important problems with the A star, how we can solve those problems, and how we can find out the heuristic function. This has been left. Are you with me? Somebody is asking that how to search. Okay, the question is how to search, how to find out the solution, that go from one place to another. Please refer the previous lecture. We have seen various ways. We have seen one method, that is blind search, such as DFS and BFS, uniform cost search, etc. We have seen, and in the informed category we have seen A star, that I had discussed today itself. Today also we have discussed. So we have seen this algorithm. Okay. So I think this answers your question. So let us see this particular algorithm. Okay. All right. So one problem was that as the DFS has a problem that it can go into the infinite depth and it would not give any solution. To tackle with that thing, we can use the cutoff on the F values, and therefore we can solve this particular problem. Another very interesting approach is to use the recursive best first search, recursive BFS algorithm or BFS algorithm. This is a slight change into this particular A star approach, and this is algorithm for this particular this particular approach. But we will be seeing this approach using an example. Let's first go to the example and try to understand why it is doing. Then we will be seeing, coming back to this algorithm and try to see that how this algorithm works. So we are going to see the recursive best first algorithm in action, and this algorithm, the important part is that it uses a number that tells that what is the alternate path available for me. What do I mean? I am going to tell you just now. So let's assume that you are into the array, okay, and then you have expanded this particular place and you find out the value is 366. How you find out 366? 366 is the actually F value, and how you find out F value? You know, this is a summation of how much you take for coming from here, how much you take, how much you have spent to come over here, and how much you are expected to spend from here. That is a heuristic function, the summation of both the things. We have seen that it's 366. So this is not a big problem. You see that here the same thing over 366 was into the A star also. So you just find out that how to find out the 360. What is this infinite? Infinite tells that is there any alternate route? If exists, then what is the cost for that? And since array is the first only, so therefore there is no alternate route. I am just going to give you a start from here. Is there an alternate route? No question arises. So therefore this value is infinite. But from the array, you have find out three places. Sibiu, Timisoara and Zarind. And for those places, if you find out the F value, they comes out to be 449, 447, 393. The same thing, okay? These values. 393, 447, 449, okay? These values are here, again, once again. You find out these values. But which you are going to expand, because in your, let me just take it to the paint. Okay, so just tell me. Okay. So what I wanted to tell you, that in your frontier, earlier was arad only, okay. Then you took it out because you have evaluated that arad, that this is not the goal state. Then you put these three things. What is Sibiu, TIMOSORA, Timisoara and Zarind. Let me just write STNZ, okay. STNZ. So what is their values? Their values are 393, 447 and 449. So luckily they are into this increasing order. They are into the increasing order. So which particular thing is going to be taken out? This is the S that has the value 393. So I would explore this thing. So when I would explore this, you see that when you explore the Sibiu, you find out 36 Arad with 646 and Pegasus with 415, Orada 671 and Villages 413. You find out these 4 new nodes. Okay. So you are only again going to put these things into this particular list, and they would be sorted based on their F values. Correct. But what is this values? What is 447 with the CBV given? CBV given 447 says that in this list, what is the next minimum value? The next minimum value is 447, because you have chosen 393, but at that time 447 was also there. It was the second smallest value. So the second smallest value is also being sent to this CBU. Okay. To restrict it, that if in case you are going down and you find something that is lesser than the 447, then don't explore that. You come back because you have some other expected part that is smaller. Are you able to understand this? In case you are exploring this CBU because this one is smaller, and you go down, and somewhere you find out that there is some path that is greater than this particular length, 447. So then you don't explore that path, because you have a path of 447 available from here. You come back and you start from here. So this is the overall idea of this algorithm. Look how it proceeds. So from CBU it has taken 646, 415, 671 and 413. So out of these values, you see that which is the smallest value? The smallest value is 413, and that is smaller than 447. That is smaller than 447. So you came back to CBU with a understanding that until you find out something lesser than this 447, you are not going to spend that. But since you find out that there is something of 443, you are going to spend this particular node. And when you spend this node, here also you send this information that the minimum available at this previous level is 415. You see now here 649, 415, 679. So therefore the target is given to this particular node is 415, because minimum is 415. If here, because on this level you find out another node with the 415, and it was expected for this node, it was expected that the distance would be 413. So if you find something of the 413, then you can go ahead, otherwise you cannot. Okay, so you expanded this, you find out 526, 417 and 553. So you see that the minimum target was 415. Now you cannot go ahead. You did not find the goal state, that is Bucharest, but you saw all the nodes that are 526. You see now 526, 417 and 553. They all are greater than this 515, the minimum which were given to me. So I cannot expand them. I have to come back here and expand these things, because I know that the smaller path was available. So I would come back here and I would cut this number because I saw that okay, it becomes problematic, and the minimum into this place was 417 I saw. So earlier I was thinking that by expanding this I am going to get 413 solution, but when I expanded this I find out no, 413 is not possible, minimum is 417. So I would update this value over here. I would put this value as a 417. You see this 417? I had changed this value. And then I would expand this thing, 415. But when I'm spending 415, at that time also I have to find out that which is the minimum into this line. I saw the minimum is 400. The minimum is 417 because the 417 came from here. So in this line 470 is the minimum. So therefore the target given to this particular thing, okay, since you are promising for the 415, go ahead. But second highest one is 417. If you find something more than 417, don't explore, because then we can follow that particular path only. Correct? Okay, so the same thing happened. Again, you find out that all the nodes are 519, 591 or 550 that are greater than the 417. So we will not explain because 417 is better. Then again we came back on the same node because okay, ye to acha tha. Earlier was good. So now we find out that 417 is suitable for the expansion, because it was although promising for the 415, but when we explored it, we find out 591 and 515. So that is not a right thing to go. Then I would expand this 417. I find out here 526 and 417 and 553. What is the minimum value? And here also you can see that the earlier it was 415, but by expansion I find out the minimum is 450. Therefore this value is modified and it becomes 450. Okay. All right. So we had expanded this thing 417. I find out these things, but this thing had been sent with the value 400. What is the value? 447, because 450 was that I found from here. And what is the minimum value available across the tree? Minimum value across the tree is 447. So I'm not putting this value over here. I'm not putting this value over there. I'm putting 447 into the place, because in my all the things I also, as I told you, that all the things are going into the frontier, and in the frontier the minimum value is 447 at this moment, because this value becomes 450. Earlier it was minimum. Okay, so then it is expanded, and here also I would send 447 because all the values are greater. Second highest value, this is giving me 417. Second highest is 526, 553. Second highest is 447. Then when I expanded this, I find out 418 with the Bucharest, and we find out the solution. This is the solution. Bucharest, I have explored the Bucharest, and that is lesser than the 447. Since it is lesser than the 447, I would accept this as a solution. But in case I have find out this Bucharest with a say 500, then I may have gone to the Timisoara and I would expanded this and try to see that what is the path that I got, what is the length that I got over here. So that may be, I think, maybe lesser than the 500, because in case I'm telling that it is 500, then how to go ahead with this. Hope you see this algorithm and you can understand this algorithm. So what is the algorithm? That there is a, whenever you go down, you are told that what is the second highest, and you use that second highest for the decision to whether you should go deep or not. So this is what the algorithm is, that recursive best first search algorithm. And so this algorithm calls itself, because recursively it calls itself. Initially it calls with the value infinite, and I think the successor is initially there is no successor, but you find out the best value, and then the best value is greater than the limit, then you say failure, otherwise you find out the alternate second lowest value and you explore that thing and you keep continuing with this. So I leave this algorithm with you, and it is very simple algorithm. The whatever I told you as an example, the same things are here, that whenever you are going to going to expand a particular thing, it is also told you that what is the second minimum available across all the available items, then that is a target. In case you see that the going forward is not going to be better than the second highest, then you stop that thing and you go to the second highest one and you explore that. You could keep doing until you find out the solution. Clear? All right, now. The IDA asterisk and the RBFS algorithm, they uses very little amount of memory, because they need to only take care of the what is only one state, what is the F value, and then based on the F value they keep expanding the thing. They don't expand much things, so therefore their memory requirement is very less. To improve the memory requirement, another algorithm, that is SMA asterisk, is there. That is simplified memory bound asterisk algorithm. That is very simple algorithm that tells that take all the things put into the memory until the memory is filled. Okay, and when the memory is filled, you have to remove something from your frontier. So how would you remove the frontier? Because in the frontier things are sorted. So whenever a new item comes, you put that into there and then you sort them. So you can drop out the sum of the things that are having higher value. So if you get something that has a higher value, you drop that item, and if you find that the something is of higher value into the frontier, you remove that item from the frontier and put this item into the frontier. Are you able to see this? I am telling one thing, that whenever you are expanding the thing, you are exploring new item, and all these items you are putting into the frontier, and F value is available with you. So what you should do? You should do that you compare whenever you are going to place any new thing into the frontier. You see that if some value is there that has a higher value, so you drop that item, you put this item into the frontier. Otherwise, you drop this item when the memory is full. If the memory is not full, new item is coming, you put into the frontier. This is a very simple algorithm, and to avoid selecting the same node for the deletion expansion many of the time, this actually expands the newest best leaf and delete the oldest worst leaf, and returns the best reachable solution. It may not be the optimal solution, but returns the best reachable solution. Okay, it gives you the best reachable solution. Okay, this algorithm is complete if the depth of the shallowest goal is lesser than the memory size, means you can put all the things. Otherwise, it may be possible that the goal node comes and you don't put into the frontier and you remove that before taking the things. But simple algorithm that actually try to use all the memory and therefore becoming very efficient. So this is another modification to this particular algorithm. So using these modification, you can say that either we can train the thing so that it can give the right answer, you can use a right memory, and therefore we can get the solution. Okay. Now my question is the same question that I want to ask, that can a system by itself learn that how to search better? What is searching? What is means how the search progresses. This is an important. This is how the algorithm tells, because search space is all the items are into space is there in front of us. But how the search progresses, some searches using different item then reaches over here. How you want to reach from the starting to the goal state, but what is the path that is defined by the algorithm. So, how to give a better algorithm? Can computer learn that this is the better way to go over there by itself? So the answer is yes. Okay. The answer is yes, that it could be possible that the algorithm can run, and this can be done by representing something very interesting, that is a meta level state space. What is meta level state space? It is something that it is something that when you are into one state and you are expanding this thing, okay, then you are expanding something. So you see the different algorithms are progressing into the different way. So if I say that every computation I take, that on this particular thing, if this computation I apply, then this is going to happen, means along with the state, if I also encode that what is the processing happening over there, so then I would be having a large number of states available. You understand? Because in one state I can apply, I can explore various nodes, possible nodes. If I exploring this node, I am going to this state. Exploring this thing, I am going to this state. This is totally different from the state space, because in the state space I am telling that from here I can take this particular move. I'm not talking about that that I am exploring this particular node, how many different nodes I am going to see. So meta level state space tells you that this particular thing tells you that how many different processing elements are there. Each state in the meta level state space captures the computational state of the program. Okay. So now you can apply some searching strategy on the meta level search space, that is a big space, to find out what is the right way to proceed. Okay. Similar to the A star, but all these things are theoretical, and finding out the solution in this way actually very difficult, because exponential number of size is going to be with us, but it is possible. Just we want to point out this, that it is possible that if you encode all the state along with the computations, it would become a bigger graph, and if you deploy a searching strategy on that, then you can find out a best algorithm that automatically can give you the solution. But for that, lot of processing power is required. Okay. And here my objective would not to find out the minimum solution, but my objective would be to find out the minimum solution in minimum number of processing steps. Two different things. Can you understand this? If going from, if the I want to say this, let's assume that this particular the task, let's assume that we have a graph, and from starting from this node, if you go somewhere and you reach somehow to the goal state. Okay, and let's assume that this is the optimal path. Okay, so algorithm A can find out this path. Say there is some algorithm, say in 100 steps. Algorithm B can also give the same answer in the 200 steps. Algorithm C can give the same answer with the 150 steps. So there could be various algorithms. So this, the target would be, target of this particular kind of search thing, that I want to find out some algorithm X that gives me the things into say 50 steps. Okay. How do you see this? All these algorithms are going to give you the same answer, same optimal answer. Okay, the answer would be same. Answer would be same optimal answer. It would be the same optimal answer. But now you want to find, now you want to deploy that that I need to spend the minimum number of steps to find out the solution. Okay, so in this way, if you change the problem into the meta level state space, then searching into that space would give you the better algorithm that would give you the answer into lesser time. Now somebody is telling, sir, will we have to define the performance metrics to compute the difference algo for the machine itself? So that is the performance measure, and going by that is actually a subset of that. Okay, here it may be possible because you are defining some performance measure. Na? What would be the best performance measure? That you don't know. So sometime independently of the performance measure, it can give you the best thing to use. Sir, please explain what does the computation step contains. Okay, the computation step would contain the trees that you are actually expanding. Okay, you know that the tree that you are one by one expanding so that you reach to the answer. Even if we have small search space, say only 5 things, so what is the search space? Okay, let's just assume that you have only 1, 2, 3 search and this kind of connection only. So if you start from here, you go here, then you can again go here, then you can go here, then you can go here. You can keep searching this in this way. So if from here you say that there are two places I can go. From here you say that I can go two places. Here then if you go to this place, then you can say that I can go two places, I can go two places, I can go two places. Everywhere you say that I can go two places. So this particular tree, can you see that how many trees are possible? There are infinite trees are possible. Okay. So therefore, although the number of steps, number of states are only 3, and connections are limited, but you see that infinite, the tree total number of trees that you can form can be infinite. That initially one tree would be having only one state, another would be only second, then third, then how you are progressing with the computation. So these trees would be telling you that how the processing is going to process. So all the trees would be there. In that search space, if you apply a searching, then you would be getting the best algorithm, and its target would be give you the algorithm, give you the right answer into the best possible way. Okay. Now we will discuss something that how to find out the heuristic function. Okay, and the heuristic function is consider it. We are going to talk in terms of a example. So let's consider the 8 puzzle problem. You know the 8 puzzle problem that I just studied, that there are these. I think that all of you have seen this. Can anybody write that who had not seen this particular puzzle? You can write I have not seen. Okay. I am not seeing any no. Yes, so it means that everybody has seen this. I have not seen. Okay. Somebody have not seen this. So these are the tiles. Okay, these are the tiles, and the number is written on them. Number could be 1 2 3 4 5 6 7 8. So when you purchase this from the market, it is like this: 1 2 3 4 5 6, and you can just slide this 3 to the upside. If you slide this 3 to the upside, this blank space comes over here at this place. So can you see this? Okay, can you see this? Then when the blank space is here, then either you can slide the 6 up or you can slide the 4 up. Okay, you can go ahead. So here what you can do, you can, if you want to put the 1 at the at this location, what need to be done? Can you tell me? You slide this 6 over here and then you slide 1 over here. Okay, then you take let us try to solve. I think it would take a lot of time for me, so I will not do this. Just by yourself you try that. 1 had moved up, then you take 3 over here, 6 down over, 2 down over, 4 down here, take 1 up. Okay, in a circular way you can take 1 here, and the 1 would be at the right position. So similarly you can find out that how can find out all the things at the same place. This is what the thing is. So let's assume that I give you this state. Okay, and we have also discussed into the lecture 1. Okay. You just once again see the lecture 1. So let's assume that this is the start space state, and this is the goal state. Okay, this is the goal state where you want to reach, means all the things are 1 2 3 4 5 6 7 8, and here some arrangement is given to you. So let me tell you that the average solution cost is 22 steps. Means if you do very well, then sometime you may be taking, because sometime I just slide this 1 over here and you have to only slide once. So average means for all the cases, if you find out how many steps is needed for the optimal solution, then average is 22 steps. So sometime more than 22 steps is required, sometime less than, but average is 22. Branching factor is near about 3. Means if this empty space is in between, then there are 4 possibilities. But if empty space is here, then 3 possibilities are there. Sometimes when the empty space is here, only 2 possibilities are there. So sometimes 2 possibilities are there, sometimes 3 possibilities are there, sometimes 4 possibilities. The average is branching factor is nearly 3. So you can find out that from here, what are the other spaces in which you can go. Okay, if the branching factor is 3 and 22 steps are there, then the tree size would be then 2 to the power 33 states are possible, because into the tree 3 to the power 33 and that is a big number. That is 3.1 into 10 to the power 10 states into the tree. That is a very large number. But if you don't follow the tree behavior, that you start from something, that you make tree and find out the solution. Instead of this, you make a graph, that you are here, then you take this place, you go to this place. You, instead of tree, if you make graph, then you need not to construct all these things. And we have discussed in the last class that there are only factorial 9 by 2 number of what is the factorial 9 by 2? Because you know not how many different arrangement could be possible. So 1 to all these numbers are, say, blank space. You can also say that it's a number 1 to 9, and then you can write on the single line, and you can find out what are permutations are possible. So there are factorial 9 permutations are possible. But we have discussed in the previous class that half of them cannot lead to this answer, because it may be possible that I can give you something that whatever you do, you would not be able to reach into this particular state. There would be something else. So therefore, total number of state is only 181,441. So this many number of states you have, and now you have to find out, given a state and given another place into the graph, how to you go from this. So this number is manageable, okay. But the problem is that if you go for the 15 puzzle, because it's a 8 puzzle now, if I increase, make it 4 by 4, now it becomes, it's a 3 by 3. If I make it 4 by 4, it becomes 15 puzzle problem. So it has 10 to the power 13 states over here. So because now, and that becomes very difficult to manage. Okay, to find the shortest solution using A star, we need to find out appropriate heuristic function. So how 33 came into the picture? 3 to the power 33. Oh, thank you very much for pointing this out. It's a mistake. So can you tell me what should be this number? It's a typing mistake. What should be the right number? 22, correct? Yes, all right. So this number is 22. Okay, it's a typing mistake. I will correct this. So it is 3 to the power 22. Thank you for pointing this out. So okay. So then very difficult to, if it is a 15 puzzle problem, then very difficult to manage these many number of states. But let's assume that we are going to solve this problem only. So how to find out a heuristic function, okay, for this? Because if this big search space, blind searching from one place to another would be very difficult. If we can find out some heuristic search, that would be doing the better job. Okay, so let me give you two heuristic function. First heuristic function is the number of misplaced tiles. Number of misplaced tiles. Okay. So here, how many tiles are misplaced? At this place there should be 1, but it is 2. At this place there should be blank, it is 7. At this place there should be, how many tiles are there? 8 tiles. How many tiles are misplaced? 7 is misplaced. 2. This is the place for 1. This is the place for 2. It is 4. Place for 3, but it is place for 3, but it is 5. Place for 4. No, I am not talking about this place. This is at this place where it should be 5. There should be 6. It is 8. So I see that all of them are misplaced. So if I find out this in this way, that H1 is the number of misplaced tiles, so I see that all the tiles are misplaced for this particular example. So can you compute this thing? Very easily. Given the things, you can compute this. What is the value of H1? Okay. Then using those particular formulations, because from this place to this place, if you say that from one configuration to another configuration, if you come, it is just a one step, and then you use the H value out of that, and then you try to make the contour and cross the contour, you'll be very easily able to reach the final solution. Okay. Let me give you another heuristic function. Sum of the distances of the tiles from their goal position. Sum of the distance of the tiles from their goal position. So sum of the distances of the tiles from their goal position. So can you help me in finding out this? Okay. So can you tell me that what is the distance for this, the first tile? First tile should be here. Okay. First tile should be here. So what is the distance? 1, 2, and 3. Okay, so for this the value is 3. Okay, second tile should be here, so the distance is 1. Okay, fourth tile should be here, so 1, 1, so it need 2. Okay, you cannot find out the distance in this way. Okay, because they cannot move diagonally, so you have to only follow 2 steps. Okay, so it is called the city block, CITY block, city block distance on Manhattan. It is called Manhattan distance. So for the 6, can you tell me what is the distance? 1, 2, 3. It is 3 distance. Okay. For the 8, this 5, what is the distance? 2. Okay. For this 8, what is the distance? 2. Okay. For the 3, what is the distance? 3 is this 2. For 1, what is the distance? 1, 2, 3. 3 is the distance. So what is the summation? 3, 1, 2, 2, 3, 2, 2, 3. So what is the summation? Can you find out what is the summation? Can we tell? 18. Okay. So this is another heuristic that sum of the distance of the tiles from their goal position. This is also a heuristic. And one important property that we want from the heuristic, that it should not overestimate. Okay. So is it the overestimation? Does the overestimation means given the problem, whether the problem can the problem be solved in less than this number of steps? Is it possible? If I give you this configuration, can you solve this into less than 8 steps? No. Can you solve this into the 18 steps? No, because you have to move 1 so that it reaches over here. It would take this 3 step, okay? But there would be, although you cannot solve into the 18 step as well, it may be possible that you may take more than that step. But at least 18 steps are required. So it is not overshooting. This is an important thing. Okay. Then one thing, that none of them overshoots. This is an important thing, and it should not overshoot. If it is a heuristic function, it should not overshoot. Okay. Then we want to expose you to the important mathematical concept, that what is the effective branching factor. Okay, you know the branching factor, that if you are into this state, how many other nodes are there. So this is the branching factor. But sometimes this branching factor is useless because you are not expanding all of them. Okay, your algorithm, how many things that your algorithm is actually expanding, that is important for you. So you want to find out how many things that your algorithm is expanding. Let me represent it by B asterisk. Somebody is asking, sir, please tell why we have not included the space for the calculating H1 and H2. Because if you put all the things at the right place, then the space would automatically be at the right place. Correct? Somebody is asking why we are not included space for calculating H1 and H2. Because if you put everything at the right place, the space would automatically be at the right space. Okay. So effective branching factor, you understood. So how to find out the effective branching factor? So this is the formulation. If n number of nodes are generated and by the algorithm, and solution is found at the depth, then if n number of nodes are expanded generated by algo, and the solution is found at the depth d, then if effective branching factor is b, then initially you have consider first item, then B item, then B asterisk square item, then B cube item, and up to D that you expanded these number of items. The general formulation is this. Let's assume the tree is in this way. And this should be equal to n plus 1 because n number of items has been generated and one item was from which you started. This should be equal to n plus 1. So when you run the algorithm, you would be you know that what is the value of n, what is the value of d, because when you find out the solution, you see that how many items have been sent to the frontier. D is what is the depth of the solution that you would be exploring. Okay, so if you know n and d, then you can put into this formula to solve, although it is a very high dimensional formula, but you can solve this formula to find out what is the appropriate value of B star. Okay, effective branching factor can characterize the quality of the heuristic function. If the heuristic function is good, then this value should be 1, because very easily you just go to the solution. If branching factor is 1 means what? Well, you are immediately going to the solution. But generally 1 is not possible. Okay. Okay, so let us see that what is happening. Let us run this. Let us run an experiment. This is given into the book. And what is the experiment? That I am running the A star algorithm and onto the 1200 random problems. 1200 random problems. Randomly I generate some configuration and I run the A star algorithm to find out the solution. Okay. And what is the length? What is the solution depth? Okay, solution depth. I think length should be depth. Solution depth. What is the distance? Okay, what is the distance? Means when I apply that this thing I want to do, what is the distance? I want to, let's assume that the distance is 1 to 24. Okay, so for 2, 4, 6 distance, 8 distance, for each of the distance, I means from the original thing, I misplace I put the another question. Look at the solution we know that what is the goal state we know. So we create the problem instances such that the distance between these two are 2, 4, 6 and 24. Similarly we can find out different numbers, and for all of them I'm going to run for all of these I'm going to create 100 cases. Two distance places, how many cases I am going to construct? I'm going to construct 100 such cases, and I am going to run this A star algorithm to find out the solution. Are you able to understand this? You know the goal state. Can you give me something that has a distance 2? Yes, you can give it, because if you know the function, you can find out that two things uh, you change at the two places. Okay, 2, 4, 6. I say you places you change those things. So that distance is 2, 4, 6, 8, 10, 12, so ahead to 24. And for each of the, let's assume I want the distance 10, then 10 distance from the goal, how many questions I am going to create? I am going to create 100 different questions, and I am solving this to find out the solution. And for each of these solutions, I am going to write these things. Means how many IDs I have generated. If I am using heuristic 1 and if I am going to using the heuristic 2. Okay, and what is the effective branching factor I get? An effective branching factor given the n and given the d, you can find out using this particular formulation summation, and this value comes out to be, for heuristic 1 the value is 1.48, initially 1.79, then 1.483636, 1.48. Sometimes you see that there is a different change, but after that when when the distance is high, you see that it is actually getting saturated at 1.48, and the value for this H2 is you see that 1.26. So if branching factor is 1.26, means less number of items are actually explored. Okay, so therefore which particular heuristic is better? Can you tell me whether H1 is better or H2? Can anybody tell? If the branching factor, if I use this heuristic and this H1 and H2, so I see the branching factor is 1.8 and 1.26. Which particular hypothesis is better? The better algorithm is one who has the lesser number of things to explore, because it is going to give you the solution in less number of steps. So therefore H2 is a better algorithm. You see that H2, and for every node the H2 value is greater than H1, so the H2 dominate H1, and therefore H2 is better than H1. You have seen this experimentally also, that H2 is, when experimentally you have generated randomly problems and find out this, that the branching factor of the H2 is less, therefore it's better. So you should think that if you make a heuristic function, if you have two heuristic functions, okay, if you have two heuristic functions, then you should use that heuristic function which provides the larger values. If it is providing the larger values, it is better to use the heuristic function with the larger values. If the value is large, then that heuristic function would be better. So till now we have understood one thing, that if somebody gives you various hypothesis function, then you should choose that hypothesis function that has the larger value for the nodes. If it does not dominate on all the nodes, then you can take the maximum also, and you can construct a new hypothesis function by yourself. All right. But we have still not talked that who is going to give you this idea that H1 is number of misplaced tiles. How you get this idea? Okay, again the question is again that how to come up with this H1 and H2. Okay, to come up with this idea of H1 and H2, we are going to talk about a very important concept that is called relaxed problem. What is the relaxed problem? In the original problem, there are some restrictions. If you remove or lower some of the restrictions, then it is a relaxed problem. Okay, consider the following relaxation related to the related to the 8 queuing problem. So I am going to talk about two relaxations. Okay, related to 8 puzzle problems. What is the relaxation? Tile could move anywhere, not only one square towards adjacent block. If I say that tile, you can move the tile anywhere in one step. It is not that you need the tile can go only one place. If I say that this is a new problem, that 7 can in one step can go anywhere, 2 can in one step can go in anywhere. Okay. If I say this, so this is a different kind of problem where I say that given this, can you create this? Yes, you would take only 1 minute to just put all these items. You see that what should be here? Here should be blank. Okay, here so you should put 4 over here. You take 4 over here, and then you start moving. What should be here? 2. You put 2 over here. Then you see what should be here. 1 should be here, to put 1 over here. So similarly, into the 8 number of steps, you would be able to solve this particular problem. If I relax in this way, if I say that tile could move anywhere, not only one square forward adjacent empty block, जो कि पहले condition था, it was the initial condition. Then what is H1? Exact number of steps. H1 gives you the exact solution. See, H1 was the same function. Means to find out H1, you see some relaxed version of this particular original problem, and in that problem you see the solution, and that solution is that solution length is going to give you the H1 hypothesis. Let me give another relation. Tile could move one square in any direction, even into an occupied space. If I say the tile can move one square in any direction, even in an occupied space, this is a different problem. It says that 7 can come here. If it is 2 is here, so then also it can come over here. What would happen? That to put 7 here, you need 3 steps that we have calculated. That how much misplaced this 7 is. To put 1 over here, I need 1, 2, 3 steps. That is we have calculated into the S2, because in the S2 sum of square the sum of the distance of the tiles from their goal position is actually taken. So now H2 is this second function. H2 would give you the exact number of steps over here. Okay, are you with me? So state space graph. This is a very important thing. State space graph of the relaxed problem is the subgraph of the original state space because of removal of some restrictions. Okay. So what would happen? The state space graph of the relaxed problem is the super graph. Okay. So it's the super graph of the original state space because of the removal of restrictions. Can you understand this? Let me tell you what I mean by this. Okay. So if I say that these Just assume the state space graph. These are the states. Okay, these are the states. Okay, you can go from here to here, here to here, here to here. Let's assume that you by having some moves you can go from here to here, here to here, here to here, here to here. There is some path available. Okay, if I say more restrictions if I apply over there, so what would happen? More restrictions if I can apply, what would happen? If I apply more restrictions, that it may be possible that this would go away, this would go away, this would go away. यही तो होगा और क्या होगा? If I remove some of the restrictions, if I impose more instruction, impose more restrictions, what would happen? Some images, some edges would some edges would go away. Are you with me? Can you see this? Because I can do these things, na? Initially I can do these things, but if I say that no, you cannot do this, what does it mean? That particular transition would not be there. So if I impose more conditions, then some images would go away. So if I say that impose less restriction, less restriction, less restriction, तो क्या होगा? What would happen? More edges. So more edges. What does it mean? Super graph. This would be the bigger graph. Super means if you have a problem and if you have a state space graph for that, if you relax that thing, so new edges would appear. New edges would appear. So you see this? Are you with me? Can you understand this? Can anybody write yes? A state space graph of the relaxed problem is a subgraph. No? Somebody is writing no. Please explain. Okay. Okay. So once again, let me try to explain this. Okay. So, please, people who have written no, please be with me and tell me that if you have a problem. I say this thing. Are you with me? That let's assume that this is the state space graph of some problem. State space means all the states are there, and if you take some move, a move, you go there. You take another move, you go here. You take another move, you go here. Take another move. So this graph would be there. Okay, there would be some graph. Are you with me? You understand that what is the graph? Okay, you understand that what is the state space graph? Okay, state space graph. Okay, if I impose more restrictions, what do I mean? If I put more restriction means what? That now you cannot go into this way. यही तो होगा. Restrictions क्या होगा? कि now you cannot take this move. Restrictions will be condition, and those conditions would tell that now from this state to you cannot go into this state. यही तो होने वाला है. So if I put more restrictions, if I put restrictions, what would happen? Less edges. Are you with me? Can you understand this? States would be there, but edges would be reduced. Edges would be reduced. You are with me? Everybody with me? Because restrictions means now you cannot take this step. If you cannot take this step, so from this state you cannot go here. So this edge would go away. Some edges would go away. Okay. Similarly, I can say that instead of restriction, I can say I can reduce restriction. So what does it mean? This was the restriction. It is removed. Now I can go. This was the restriction. It has removed. I can go. Because restriction has removed, there is a new path over here. Because the restriction has removed, new path has created. Are you with me? So if you reduce the restriction, you get a super graph. by super graph I mean that with the same nodes you are getting more edges. More edges. You understand this? Can anybody write yes? Do you understand this? Very good. So I am telling this part only that the state space graph of a relaxed problem means when you are relaxing some of the conditions is going to be super graph. Okay. So if you find out the solution into the super graph, okay, solution to the original problem, okay, if you find out a solution in the original problem space would work for the relaxed setting. Means if you find out the solution into the original graph, okay, if you find out the solution into the original graph means graph that contains only say this time blue lines, and if you apply into the new graph that contains blue and red also, then that solution would also work here. Okay, if you find out a solution, say you want to go from here to here, and you say that this is the solution, here to here, this is the solution. So this solution would also work into the relaxed version. Okay, this solution would also work into the relaxed setting. However, there could be better solution in the relaxed setting. However, in the relaxed setting, there could be better solution. What does it mean? That to come, let's assume by relaxation, you got that there is a direct edge from here to here. So in the relaxed setting, you can find out this path also, but this path was not available into the original solution. So in the relaxed solution, you can find out the smaller solutions. Okay, you can find out the smaller solutions. You understand? The solution in the original problem space would work for the relaxed setting. However, there could be better solution in the relaxed setting, having lower cost. Lower cost? Lower cost means no overestimation of the actual cost. Lower cost, actual cost is going to be only greater than this. Okay? So if ये तो बढ़िया बात हो गया. Means original problem, you define these kind of relaxations, and then you can solve those problems, because solving the relaxed problem is easy, because you say that now if you take the eight puzzle problem and you say that the tile could move anywhere, or you say that tile could move one sequence in any direction even into the occupied space, you are getting a different kind of graph. If I give you a problem, you try to solve on this new space, and you find out the solution. That solution is not going to overestimate, and therefore it would be, since it does not overestimate, it can be used as a heuristic. Therefore that can be used as a heuristic. So a solution in the relaxed problem space could be used as a heuristic. That is a one thing. So I want to tell you at this particular point, very important concept, that given a problem you find out a relaxed version, and in the relaxed version you find out the solution. And that solution you can use, the length of that solution you can use as a heuristic to go forward. Okay. Sometimes it will be possible that multiple heuristics are there. So if multiple heuristics are there and you don't know that which one is better, then you can find out the says none actually has the because I told you that if multiple hypothesis heuristics are there, then you should use that heuristic which has the higher value. So if multiple hypothesis heuristics are there, you can use the maximum of that value on every node. You just apply this max function to find out the heuristic value. That would be a better strategy. So I told you that how to find out the heuristic problem. Okay. So this was the one approach where you have relaxed the problem, and another approach could be to find out this hypothesis function is to use sub problem instead of solving the complete problem. Now you are going to solve only small problem. There you have relaxed the conditions. Here you are not relaxing the condition, but you are telling that I only care about these four things. That I want from this state, I just want to reach to this state. I don't care about these locations. I just care about 1, 2, 3, 4. If I can reach into this place, then I'm okay. Okay. So this is only if you go into this way. So this is called the sub problem. This was the original, instead of original problem, this is a sub problem you are solving, because you are only solving half of the part. Although if you want to find out all the things at the right place, then ultimately you also have to solve this thing, because 1 2 3 4, so 1 2 3 4 should also be come at the right place, and also these things could also come at the right, these things should also come at the right place. So although they are not at the right place, but you think that your solution is right, and this is called the sub problem. So only one to arrange 1 2 3 4. If you look here also, you can find out some heuristics. How can you find out the heuristics? I'm going to call a new term that is called the pattern database. It store all the possible sub problems that are possible and their solution cost. From here to here, what is the solution cost? And then given the problem, you can use this particular solution cost, because this was easy to solve and somebody has solved this problem and given you all these values, so you can use this as a heuristic. So then you can ask that similarly, if I can ask the things for 1 2 3 4 1 2 3 4, then I can also make the pattern database for 4 5 6 7 5 6 7 8 also. I can find out the pattern database, and then to go forward, I can use the solution cost of that thing as a answer. Okay. So that would also be perfectly all right solution. Okay, you can use that instead of using 1 2 3 4. Instead, I can say that I can use only 1 2 3. That is also possible. Here I am telling 1 2 3 4. That is fine. So solution cost for 1 2 3 1 2 3. Okay, and the solution cost of 4 5 6 5 6 7 8 would be two different databases, and then and their cost you can use as a heuristic. And then you can also ask that can we add the cost for 1 2 3 4 and 5 6 7 8, means in the one database you find out what is the cost for this, in another database you find out what is the cost for this one, 4 5 6 7, and you add those things to find out the cost from going from this place to this place. But you cannot add this. You cannot add this because going from 1 2 4 3 this position to this position, you need to change this position somewhere, and those position would also need to be changed into 5 6 7 8. So therefore, there would be some of the moves which are actually double counted. So you cannot add this. But if you say that, but then again there is a solution that tells that instead of using the from here to here how many steps are required, instead of using those things, you just use that from here to here. If I go, then how many times I am moving 2 4 1 and 3 only. Can you see this? If you are into this configuration and you want to find out that I want to go into any of this configuration, then you know that sometime you may be shifting 4 5 7 and 8 also. You don't count them. You don't count them, and in this pattern, and you create another database where you put the disjoint pattern database. Here, instead of using the solution cost, you put the number of moves taken by the 1 2 3 and 4 only. Then in that case you can find out, if two database you have, one database is for 1 2 3 4 and another database for 5 6 7 8, then you can add the corresponding numbers, and then you can find out the solution. So this is the another way of finding out the heuristic, and using the sub problem approach. That is also equally valid notion. The last slide, that actually another way, very interesting way, because here you can apply the machine learning to learn about the heuristics. And in the machine learning, you know that you have to provide features, because if you have a experience, if you have solutions, because a lot of, let's assume that you have a lot of 8 puzzle problem available, and for each of the 8 puzzle problem, you have the solution. Okay, lot of 8 puzzle problems are there. For each of them you find out the solution. Then you can find out the H value for each of the nodes, because given the solution in the solution path for each of these nodes, you can find out what is the H, because you know the solution. You, for the last item it is 0, then 1 2 3 4, you can assign these things. So you can find out the H value for all of them. And now how to learn this? You to learn this, you can apply decision tree neural networks or something else, some other SVM, anything you can apply to find out that some regression you can apply to find out that what is the appropriate value. Okay, given a node, now given a node, you would be able to find out what is the H value. But to do so, only node would not be important. Okay, you need to find out the appropriate feature. And what could be the feature? For a given state, there would be a feature. What could be the feature? Instead of state n, we have to use feature, say x of n, that is a number of misplaced tiles. Given a state, you tell that this is the first feature. First feature is the number of misplaced tiles. Second feature could be the number of pair of disjoint adjacent tiles that are not adjacent in the goal state. Number of pair of adjacent tiles जो यहाँ पे हैं, but they are not adjacent into the goal state. You find out this thing. Another feature. Using various features, then you sometimes want to find out want to apply some model, and one such model could be a linear combination model where you see that C1 x1n and C2 x2n is the right way. How to find out the C1 and C2 is the problem of machine learning. So you provide the samples that for these things what is the H value, because you know for the sum of the states what is the actual value. So you provide the feature values and you provide the H values for all the states, and then your machine would learn and tell that what is the right function to fit over that. So these are the ways that you can explore to find out the heuristic function. Please note down that the heuristic function is a function that never overestimate. If it does a overestimation, then there would be a problem. So that's all for today. Any more questions, please let me know that if you have any more questions. Sorry, I have took more time than required.